A word from our sponsor. Waterfall Security Solutions is the OT security company. Our latest product, Waterfall for Intrusion Detection Systems, enables safe connections between industrial intrusion detection sensors and the industrial networks those sensors monitor. Like all Waterfall products, Waterfall for IDS provides physical protection for important OT and industrial networks, not just software-based protections. For details, please visit the Waterfall website. Thank you for your attention.
The Industrial Security Podcast with Andrew Ginter and Nate Nelson. Sponsored by Waterfall Security Solutions.
Welcome, everybody, to the Industrial Security Podcast. My name is Nate Nelson. I'm here with Andrew Ginter, the Vice President of Industrial Security at Waterfall Security Solutions. Andrew is going to introduce the guest and the subject of today's show. Andrew, how are you?
I'm well, thank you, Nate. Our guest today is Roman Arutynov. He is the co-founder at Xage Security. Our topic is blockchains for industrial security. So let's listen in. So Roman, thank you for joining us. Our topic today is industrial blockchains. And, those are two words that I'm not sure I ever expected to hear in the same sentence. Can you start at the beginning? What is Xage and what have you been developing and who in the industrial world is using it?
Thanks for having me, Andrew. Happy to talk about Xage and what we've been up to. So let me just start from the beginning. Xage has been around for about 3.5 years. What we're up to is we're providing a universal identity and access management solution as well as a data security solution to industrial operators. Think of our solution as really an identity access management and data security fabric that spans across the industrial field operations, whether they're in oil and gas, utility sector, manufacturing, that controls all the various interactions, users to machine, machine to machine, application to machine, as well as how applications are consuming the data. The product is fundamentally built on top of a blockchain technology, and there are a few reasons for why we chose to do that, taking into account requirements from our customers, the fact that they have distributed operations, the fact that they have mission-critical operations where availability is of utmost importance, and the fact that they need to be all secured given the digital transformation efforts that they're all undertaking. So we work with power companies, utilities, oil and gas companies with large field operations, manufacturing firms as well. And I can give you a few examples as well of how they're implementing our solutions.
So I think that because this is a form of technology we haven't hit on in this podcast before, we should briefly describe it. Blockchain is a technology that's really only just over a decade old. It was invented in a white paper in 2008 in association with the cryptocurrency Bitcoin. And the basic way that it works, I'm not going to give a whole history of blockchain here, is the blockchain is a ledger. It's a set of records. It's a way of organizing data. So data is grouped together in what we call blocks, and each block is linked to future blocks with future data by cryptography. So each block contains the cryptographic hash of the block which came before it, and in that way, you can essentially prevent data from being changed on this ledger because, as we know, every time you change any bit of a data, the cryptographic hash that results from it changes dramatically. So the blockchain really is just a way of keeping track of data and preventing past data from being changed without making it very apparent.
So that's right. In this case, though, instead of tracking the movement of money, we're working with permissions is what Xage is up to. How does that work? I mean, a lot of people, they think of the Bitcoin blockchain as keeping track of transactions. Mary gave 2 Bitcoin to George. But you can think of the ledger the other way around. Instead of keeping track of transactions, you can also think of the ledger as keeping track of balances. Mary has a balance of 10 Bitcoin. George has a balance of 0. After the transaction, Mary has a balance of 8. George has a balance of 2. So if you think of it as keeping track of what people have, my understanding of what Xage is doing, among other things, at the very simplest level, is they are keeping track of what permissions people have, as opposed to what money people have.
You know, Andrew, I have never heard of blockchain used in this particular way, and I have some questions.
Well, let's listen in for a while and work through your questions. I had a lot of questions as well. My next question to Roman was, can you give me an example? So let's listen in. Can you give us a specific example? One customer, what they're doing with your stuff?
Yeah, there are a number to name, but I'll start with General Electric. So we work with the GE Renewables team, and GE has operations across 80 countries, about 30,000 sites and 20,000 people interfacing with those sites, employees, contractors. The challenge is all of these sites, think wind turbines, large SCADA systems, have workstations, have relays, have various telemetry units, SCADA systems across all of them. Some of these systems, in some cases, these assets are owned by the actual owner of the asset, and GE simply operating it for them. So there's a need to control access both from GE folks, GE contractors, and actual third parties or the owners of the asset themselves. It becomes a very large multi-party access control challenge across very distributed type of a geography. So when you start thinking of that and how to solve this type of a challenge, you have to start thinking of the identities of the folks, identities of the machines, policies of how they're out to interact with each other. And that all requires trust to be built among users, devices, and the policies that are being enforced. So Xage has implemented a security fabric. We're rolling that solution out with GE. And that security fabric essentially is able to validate the various identities of the users, whether they're coming from GE, whether they're coming from another third party, be able to authorize according to a policy, and be able to then enforce strict access control of what they're allowed to do to certain assets. Also creating an immutable audit record, so there's no question or concern of any malicious activity, and everything can always be double-checked after the fact. So our Xage Security Fabric, the blockchain technologies that it uses, is the key enabler to make this happen. Now, and the reason is because there's multiple parties involved that don't necessarily trust each other. It's highly distributed. You need to have authentication authorization at the edge and across the various edges. And it's highly available.
So you mentioned passwords. I mean, the usual way, the traditional way to control access to things like PLCs or even, software packages is passwords. What's wrong with using passwords? Why do we need a blockchain?
That's a good question, Andrew. So what we're finding is passwords are actually quite a bit of a challenge, present quite a bit of a challenge in this industrial space. Fundamentally, what's been used on most PLCs and RTUs is local accounts and local passwords. Those local accounts and local passwords then are shared between people. They can leave with people once they leave the company. these passwords can be need to be looked up constantly. So as a result, most operators simply put every RTU and every PLC to have the same account, same password across 10,000 locations, and that presents a big security challenge. Once malware penetrates into the environment, it can quickly spread and attack all the various PLCs and RTUs. The other concern there is the passwords can be changed by unauthorized users. So one of the examples we've run into is when a technician went out to, drove out, and I think actually flew out to a remote site just to figure out that the technician before them has changed the password. They had to fly back to figure out what that password was. The previous technician already left the company. They had to track him down to figure out what that password was so they can do work and continue their maintenance operations. So that presents an operational challenge as well. So, and not to mention, many of the, in fact, what we're seeing, 80% of the devices out there don't even have passwords. They speak an industrial protocol that does not use a credential at all, and that presents yet another security challenge as well. As it may improve operations because of you don't even need a password to get in, but in today's context, creates a very large security problem.
Okay, some of that made sense to me, but I think that his example about all the PLCs and that were hooked up to the same accounts may be a little bit of a straw man argument because, of course, the simpler solution, it seems to me, of when hundreds of PLCs are all hooked up to the same account is just to not do that. Do we really need a whole blockchain system to get around what seems like a pretty simple problem?
Yeah, I mean, there are solutions out there. There's Radius, there's Active Directory that we've talked a lot about. These are central password managers that have been used for decades. Active Directory is kind of Windows centric and so might not be a terribly good fit for PLCs. Radius, though, was invented in, I think, 1991. It was used extensively for a long time for internet dial-up. So to authenticate a user coming in with a password saying, do you have an account on this dial-up provider? This was back 30 years ago when the internet was young and you still used a dial-up modem to get on the internet. So that was, in fact, my next question to him, saying, why do we need blockchain? What's wrong with these central managers? So let's listen in. I think I know some of the answer already, but for the record, stuff like Radius systems and Active Directory controllers manage passwords for devices. Do they not fit into this space?
That's a very good question as well. So for various reasons, Active Directory can't be implemented directly into the industrial space. Some of these reasons are one, that the devices themselves, majority of them, do not speak Active Directory. So they don't support a centrally managed role-based access control type of a methodology. They simply support local accounts. Two, if you were to take an Active Directory, if you think of an Active Directory implementation, Active Directory is designed to be held and hosted in a data center, protected by a fortress of firewalls so that your crown jewels, all your accounts are not compromised. Well, then that requires every single RTU and every single PLC to have direct connectivity, two-way connectivity into the data center where Active Directory is hosted. And that's just not how things are designed. Things are designed to be, in many cases, isolated, designed to the Purdue model of network architecture, and that creates challenges with implementing Active Directory or, in fact, Radius-based solutions as well. So the right way to approach this is to really make identity and access management, authentication, authorization available where the devices are in their local networks where they're used. And that's exactly what we do. We create a distributed identity and access management solution using a blockchain that's tamper-proof. It doesn't need to be protected by a fortress. It can withstand, being hosted in edge conditions across the entire field, so that your authentication, authorization, and enforcement can happen right there. We actually went to great extent to make sure that our system can interoperate with existing and legacy equipment. So whether it's a new IoT device, whether it's something that's been deployed there for 20 years, we have methods of enforcing access control after authentication and authorization that involves proxy services, the ability to filter data based on unique identity of the user or machine interfacing with that asset.
You know, what Roman said, the example he gave of a system that could potentially track an unauthorized change to a password, that seems to me to be a really practical use of blockchain. Because what is blockchain other than a way of keeping record of what exactly has happened at what locations and at what time over the history of a network, and a way to prevent changes to that history retroactively. So that makes a lot of sense to me. But I'm wondering, Andrew, is this maybe an excessive use of blockchain? Like, blockchain is this exciting technology, and we're all talking about, blockchain for this, yada, yada. But it brings me to the question of, is this blockchain for blockchain's sake, or is there a real need in industrial security for this specific type of implementation, do you think?
Well, let me say a couple of things. One is, the example you gave of the ledger keeping track of stuff, that's what people tend to fixate on for Bitcoin, because the ledger is vitally important. It's how much Bitcoin I have. It's how much money I have. And I really want that to be kept track of correctly. But there's many other aspects to blockchain. If all we needed was a central ledger, we could use an IBM mainframe in a bank. We don't need, blockchain running on PLCs. And so there's many pieces that have to come together in order to call something a blockchain. And it seems to me that the piece that Roman is exploiting heavily, maybe not exclusively, but certainly heavily here, is the intrinsically distributed nature of the blockchain. Yes, we need to keep track of a ledger saying who's who and what permissions do they have, but the examples he's given so far all speak to a highly distributed implementation. CPUs keep getting cheaper. There's more and more and more of them. There's thousands and tens of thousands and hundreds of thousands of CPUs in the implementations that Roman is looking at. And we want to be able to distribute the knowledge of who's who and what permissions do they have, so that each of these hundreds of thousands of devices does not need continuous online connectivity to the central, the IBM mainframe in the bank saying who's who. The intrinsically distributed nature of the blockchain seems to be what one of the points that Xage is exploiting heavily here.
All right, so it takes advantage of the natural distributed quality of blockchain, but I'm still a little bit hazy about how exactly the system works and how each part of it interacts with other parts of it, Andrew. Can you clarify?
In fact, let's go back to Roman, because I asked him a question about that next, saying, can you give me an example? Somebody flies into the substation. What's it actually feel like using the Xage fabric? So can you give me a physical example? Let's say, Fred walks up to a PLC that he's authorized to do something to. How does he identify himself to that PLC? How does he connect to the PLC? What actually happens? Does he plug a laptop into it? What happens here?
That's a very good question, Andrew. So the way that this works is, typically they're accessing PLCs over a network, even locally in that environment. Even if they go on site, they plug into a switch or to some sort of network to access that PLC. And they do so with their programming tool. Now, when Xage is installed, we will block that access. We have a Xage enforcement point that's defined that blocks access and requires authentication and authorization for any of the interaction to go through to the PLC from the technician's laptop or from the workstation. So what they're need to do first is they need to authenticate with Xage Security Fabric, and they can do so using a variety of methods. Typically, what they do is they open a browser, they type in Xage at comment or Xage at ge.com. Then they need to then provide their credentials. And by the way, that Fabric node is hosted in that local environment, so authentication is happening right there very quickly, regardless of connectivity. Xage Fabric nodes right there in that local environment, able to authenticate and authorize them. So they provide their credentials. In some cases, it's username and password, and in other cases, they also put in other factors, card key, or a smart card or anything like that. And then after authentication, they're presented with a number of options that they have access to. So a number of PLCs on that site or other sites they actually have access to and are allowed to access. They then request access to that PLC, and communication goes through to the Xage enforcement point. Then now they're allowed to access and perform certain types of tasks, whether it's reads or writes, down to granular parameter level, based on their identity and their policy.
Well, that makes sense. In these industrial environments, though, there is not always connectivity with a single switch that a local fabric node might be connected to. Sometimes devices and switches are connected to each other, as much as several layers deep. Can the fabric work in a daisy-chained environment?
Absolutely. So what we deploy out into the field or into these environments is what we call the Xage Fabric nodes. And Xage Fabric nodes themselves can be daisy-chained and can go all the way down through into the lower levels of the Purdue model, lower levels of the network architecture, and provide authentication and authorization services to the devices out there all the way at the edge that may only be able to communicate on that local network. So each gateway is proxying one layer at a time. Each fabric node, I should say, is proxying one layer at a time. It has the directory service hosted on it. That directory service is being synchronized through the blockchain and providing authentication and authorization services for the devices in that local segment.
Okay, Andrew, I have a question for you. If we do, in fact, have a number of devices daisy-chained, as you guys are talking about in your example there, does that not introduce a single point of failure in the system, right? Earlier in your interview with Roman, he was sort of describing that problem of when you have hundreds of PLCs connected to the same account, right? And so if you breach that account, you've got access to all the PLCs. Is daisy chaining not going to induce the same sort of issue for all of the devices in a chain? Because the chain that's furthest out on the edge, if it gets breached or if it's vulnerable, suddenly it's a problem for the next 12 or 100 devices along the chain.
That's a good question. There's actually two questions buried in there. One is about daisy chaining and vulnerability, and the other one is about password management and vulnerability. Let's deal with daisy chaining first. Don't misunderstand my question to Roman or his answer. I did not ask him, does Xage require you to do daisy chaining? In the industrial world, think smart meters. Not every smart meter, every power meter in a city has internet connectivity. It may not have a good cell signal where it is, but it might have a signal to the next neighbor's smart meter. And so these smart meters, are built to look around. If they can find their smart meter network signal, great. If they can't, Try and talk to a neighboring meter and ask them, do you have a signal? No, but I got another neighbor over there who does. And they can daisy chain through each other in order to get connected to the smart grid network. This is not something that Xage introduced. This is the nature of smart meters. It's the nature of PLCs. With PLCs, we see a lot of serial connections. We see a lot of exotic connections. Some layers in the architecture have Ethernet, Internet protocol, not internet connectivity, but internet protocol communications, conventional network communications. And they tend to be connected to devices that don't have that, but they have some other connection to those devices. And those devices might in turn be connected to even more devices over some other exotic protocol. This is not something Xage has done to their customers. This is the nature of the beast. And my question was, can you work in that environment? And his answer was, yes, of course. That is the environment we work with. We have to work in that environment. That's, yes, of course. To your question of, does this architecture introduce vulnerability? Well, all connections introduce the opportunity to propagate attacks from one device to another, yes. But, in the modern world, all of these devices are connected. And so whether they're connected by a daisy chain or whether they're connected because each of them has an IP address, in a sense, is irrelevant. They're all connected. And yes, attacks propagate, and this is why we need security. And to your, to the implied question of a single point of failure, if we breach the password manager, whoever's maintaining the ledger, can we start tampering with stuff? Well, A, blockchain, has some prevention from, tampering with the ledger. But B, any central password manager, if I steal an administrator password and log into a password manager like Active Directory or Radius or anybody else and start changing people's passwords, well, that's how the password manager works. The password manager buys us the power to recover from certain kinds of failures, forgotten passwords, people left the company, to change passwords so that people who have left the company don't have the password anymore. But it costs us in terms of this central vulnerability. What it means is that we need to harden and protect our password managers fairly thoroughly. And as Roman has pointed out many times, they of course have done this. They've made their Xage Fabric nodes, the ones that manage the ledger, as close to impenetrable as they can. We've been using the word blockchain. Let's dig into it a bit. How do you fit permissions into the blockchain? There's lots of different kinds of blockchains. What's yours look like?
Yeah, that's right. So there's a number of blockchains out there, and we've looked at quite a few of them before making our design decisions ourselves. So the biggest difference perhaps is that there are public blockchains and there's private blockchains or cooperative blockchains. In a public blockchain, the participants are not necessarily trusted. Think of things like Bitcoin there. And those blockchains tend to be very resource intensive, CPU intensive. They require mining as a proof of work methodology to ensure that the participants are doing the right thing. We don't utilize that type of a blockchain. It doesn't quite fit into the industrial space, given the constraints, and there's no need for it anyways. What we use is a permissioned blockchain, a private implementation of a blockchain that gets implemented by the customer themselves. So it's hosted into the customer environment. That blockchain is part of their operation. They can invite others to cooperate with their operations as well. But every participant in their blockchain is explicitly permissioned, so it's trusted. And what we provide, and the benefits of that is the challenges that we solve and the resulting benefits is that even though you have participants who are permissioned explicitly allowed to join, you still need to ensure that the transactions and interactions that they're performing are agreed upon with consensus. They can't be tampered or spoofed, and do that across not just their own operation, but perhaps also operations of other vendors that they rely upon.
You mentioned Bitcoin, I think. I mean, that's the blockchain that springs to mind when you hear the word blockchain. One of the big criticisms of Bitcoin is how much, electric power it sucks up. How many computing resources need to be devoted to verifying these transactions. Every change, consumes megawatts, it seems. In the industrial space, a lot of our equipment is resource constrained. There's not high-powered CPUs. They may not be powered. They may be solar-powered. Can you talk about your blockchain in a resource-constrained environment?
That's a good question. So as I mentioned before, so the Bitcoin is a public type of a blockchain that requires this proof of work methodology for consensus, which is CPU intensive. It requires mining to extend the blockchain. Now, in a permissioned or private blockchain, you don't need the proof of work type of consensus. You utilize, in fact, we will utilize more of a proof of authority, since every participant is permissioned, is explicitly permissioned to be part of the blockchain network. A proof of authority mechanism is consensus mechanism is a lot more resource efficient. There's no CPU intensive cycles. Think of it as essentially validating the integrity of the data with neighboring nodes. Xage has improved that to a greater extent. Consensus doesn't need to be gained with a majority of neighboring nodes, but rather neighboring nodes in its hierarchy. So if you have, for example, a few, let's take a utility operation. If you have a substation, you can deploy a few blockchain nodes in there, and consensus can be gained within that blockchain, within that substation itself, and then propagate through the hierarchy all the way up to the higher levels, like into the control centers, into the data centers, where the ultimate reconciled against the broader ledger. So you create a very resource efficient way of recording transactions at the edge, and then being able to record them gradually as they go up the hierarchy into the control center and data center. We can run our Fabric nodes on devices as small as a Raspberry Pi over low bandwidth communication links, just because of the hierarchical nature of our implementation and the fact that we use a proof of authority consensus method.
Okay, Roman mentioned the word consensus there, which has tripped me up. I'm trying to figure out how consensus would be achieved in a private company where the blockchain is essentially centralized, right? Consensus, in the conventional sense as it's applied to blockchain, means quite literally that 50 plus 0.1% of a network agrees on the reality of the blockchain, right? If you have 100 people and 51 of them say, this is the correct version of the blockchain, and 49 of them say this is the correct version, then the 51 version counts as the blockchain, and then the 49 version, it essentially doesn't exist as a result. So I'm curious what exactly Roman means by consensus when there is only really one entity controlling the entire network, which is the company that owns it.
Well, I did not ask Roman precisely that question. We did talk about consensus after the recording session finished. Let me give you my best answer, but put a big I think around this, around all of this. First off, proof of authority is a thing. You can Google it. It's not something that Xage has made up here. It is where consensus is achieved not by proof of work, but by proof of identity and by the authority that has been delegated to certain identities, certain nodes in the network. What it means is that higher authority nodes can approve, new ledger blocks. They can approve those blocks for distribution through the rest of the blockchain. There is, and there's another element to that. When Roman talked about consensus about in nodes in a local geography before that, the ledger changes propagated to other parts of the world. If one of those nodes fails, part of the point of consensus is not just approval, but local distribution for redundancy purposes, so that if one of the local nodes fails, the other nodes have the ledger change that's been approved locally and can propagate to other higher authorities for approval to propagate into the rest of the world. I did ask Roman, our next topic, my next topic with Roman has to do with, you said, what happens if there's a single vendor and it's single authority and they control everything. It gets more complicated when there's multiple vendors involved. So that was my next question to Roman about the multiple authorities question. So let's listen into that. So you've described a blockchain where decisions about what's allowed, and these are important decisions. You're making decisions about permissions, who's allowed to do what. You're saying these decisions are authorized in some sort of hierarchy. What does that mean when we're talking about a relationship with external vendors? You mentioned GE. There's lots of vendors in this space who want remote access into stuff. Who authorizes what in that space? How does that work? Can you give us maybe an example?
Oh, sure. So I'll give you a couple examples there. So we're able to essentially create our fabric hosts the identities of various users, devices, and applications, and in some cases data as well. So we can take those identities from various sources. One of them is those identities can be defined directly in our system through our policy manager or the Xage manager. It itself is an identity access management solution. We can also integrate with Active Directory, LDAP systems, and various other identity systems that the customer may be already using. And also integrate multiple factors. So now if you have multiple participants or multiple parties, we can create a way to integrate with identity services that are hosted by those parties themselves. And then through our Xage broker, be able to suck out all that information and move it into our fabric. Now the operator gets to layer on policies of who gets to do what, and also move that into the fabric. The policies can be defined in the Xage manager itself on top of the identities that we sucked out from various identity sources. Now what that creates is ability for the user to show up and use their true identity. You don't need an account on a GE system, or you don't need an account on a ComEd system to be able to access devices. You're in fact able. You can use your identity your identity from the enterprise you're coming from, and be validated against the policy that's been created for you by the owner or the operator of that asset to access and perform various interactions with that asset.
Another thing that I've never really understood about blockchain is, the blockchain advertises itself as a distributed immutable ledger. So, you've mentioned the benefits of an audit trail. So you can, we know who's changed what permissions, who was responsible for a change. But, in resource-constrained environments, if you have a little PLC out in the middle of nowhere, or worse, a protective relay or something, a really specific purpose device, does it have enough storage to store all, the entire ledger for all of the 10,000 devices in the system for all time?
Good question. So we don't actually require any changes to the PLC itself. We don't store any of the block fabric information, identity information, and certainly no blockchain component on the PLC itself. In fact, we interoperate with existing assets. What the fabric nodes are hosted on top of, essentially think of them as industrial computers or IoT gateways that are residing in that local network. So with that in mind, no change to the PLC. In fact, we can get dropped into the same environment without requiring any of the assets to be changed. So that simplifies deployment quite a bit. The other point that I wanted to make is that even that IoT gateway that's hosting the Xage Fabric node is only hosting the relevant parts of the Fabric node that are applicable to that geographical location. I mentioned the hierarchical concept of our Xage Security Fabric implementation. So only the information about the relevant users and relevant devices and the relevant interactions in that specific geographic environment is hosted on top of that IoT gateway and the Xage Security Fabric. Now, at the higher levels of the architecture, where you may have more storage, the broader Xage Security Fabric with the broader set of identities and policies and devices is actually hosted, and that typically happens in a control center or in a data center itself.
That brings me back to something else you said. You mentioned that you could sort of drop this into an existing substation. The first impression I had when you started talking was that this was something that the vendor had to build into the products, like the PLCs, before deployment. But you're talking about dropping it in after the fact. Can you actually do that? How does that work?
Yeah, so we spent quite a bit of time actually making sure you can drop it into after the fact. And if you think about it, the biggest challenge is in doing so is actual enforcement. So you can authenticate with our Fabric node. It can authorize you, but how do you actually enforce access control? If the PLC itself doesn't have an enforcement mechanism, how do you actually enforce? So we've created a variety of methods to do so. In fact, there's three sort of categories for how we go about that. One is we have a proxy service where the communication with the PLC is actually being proxied by the Xage Security Fabric as well. So that in that situation, you can't go directly to the PLC. In fact, the proxy has changed its password to something cryptographically secure password can be done per session. And so you're forced to interact with our proxy first. And that proxy only permits you to access certain PLCs or certain devices and only do certain things. Now, there's a category of PLCs that don't even have passwords. So how do you restrict access to something that doesn't have a password at all? So here we created what we call the Xage enforcement point. It's an inline filter. Think of it as a bump in the wire. It understands the communications going through, matches it with an identity of the device that's sending that communication, the application program that's sending that application. And before allowing any of that communication to go through to the PLC, it requires the user of that application, of that machine, of that laptop, to authenticate with a Xage Security Fabric, provide credentials, look up policy, and then only allow certain things to go through. think of it as a bump in the wire filter. In other situations, in the third category, we actually install accounts on per session basis and based on an identity of the user. This is helpful with workstations where they have access control is provided through local accounts. In many cases, these workstations may have thousands of accounts. If the operator really wants to track who's doing what and control access based on an identity, they'll have to create thousands of accounts on these machines, and potentially thousands of these machines. So our system automates all of that, right? So you authenticate with our Xage Security Fabric. We install an account for you temporarily on that machine, on that Windows workstation, and only give you certain permissions to do certain things. So three main methods: proxy, filter, and account management.
Roman's answer, not the one he just gave, but the one before that, I think is pretty interesting. It sounds like his firm is taking a page out of Bitcoin's book, because the way that storage works with them seems to me to be pretty analogous. In Bitcoin, everybody has to store the blockchain locally on their systems, or else the whole network doesn't work. But not everybody can store all of the information on the blockchain. So there are what's called full nodes, which have everything, and then lightweight nodes, which are more accessible to everybody, only containing certain information, header information, so who paid who, yada, yada. In this system, it sounds like what he's saying is that the central control center, the data center, needs all the storage to hold all of the information about the network, but that local industrial computers only holds what's relevant to them. So in that sense, it's pretty analogous to me to Bitcoin.
It's interesting. I was more interested by the second part of his answer about how do you enforce permissions if you haven't changed anything, and I wanted to sort of reinforce his answer. He gave three scenarios. One is where I say I need to log into this PLC. The PLC only has one password. There's only one account on the PLC. And so the Xage Fabric goes out and changes that password to a one-time password. It gives me that password. I log in, I do my thing, I log out, and Xage changes the password back to an unknown password. Nobody knows the password. Xage is the only way to get in. So, I've seen that on other kinds of password managers before, but it's not very common. And the second point was the bump in the wire, which is, vaguely like a firewall. You authenticate to the bump, and the bump allows your communications to go through thereafter, and looks at the communications like a firewall does and decides, is each of these kinds of communications allowed or not, depending on the permissions. And the third one, and they've built all this into the same the same system. The third one is basically for Windows-like systems or even Linux systems, which is rather than connect to a domain and incur all of the overhead of managing domains the way in the Windows world, Xage would log into the system, create an account for you right then and there. You log into your account, you do what you need to, you log out, and Xage deletes the account. It vanishes. These are all ways that these permissions can be enforced after the fact without building the Xage infrastructure into your system, into your industrial control system to begin with. But all of that is talking about users using the system. My next question to Roman was about machine-to-machine communications. So that's great for users who are accessing, devices and systems. But in, a lot of industrial automation, there is, there's the SCADA server constantly pulls data from these PLCs all day long, every couple of seconds. The historian server constantly pulls data from the SCADA server, or sometimes directly from the PLCs. What do you do about these systems that are talking to each other, but there isn't necessarily a user involved?
Yeah, that's a good question, Andrew. So a good example of that is actually our work that we're doing with Commonwealth Edison over in Chicago, where they have a project going on around distributed energy resources and microgrids. their interest is to be able to essentially create microgrids throughout their territory and enable communities to exchange energy with each other inside a community as well as across the community with various aggregators, and then reconcile that also with the larger distribution area network and the power that it provides. So here you have assets, think of it as solar, wind installations, you have buildings who are consuming that power. You need to be able to tightly control which inverters, which batteries, systems, which applications are allowed to participate in this energy exchange system. And again, this is happening both within a microgrid, across a microgrid, and with the larger distribution service provider, the utility. So what we do is we start right at the beginning, right at the machine itself. We create the identity for the machine to create trust for that machine. We fingerprint its network configuration, its system configuration. We ensure that fingerprint is then tamper-proof and is ultimately used as an identity for that machine. If the configuration changes, that machine is no longer trusted until the identity is updated. Then we create a policy of which inverter can interact with which meter, which microgrid controller, which substation, and create actual enforcement points at each one of these locations to strictly control that access. And that now can expand also to other sites, not just a single microgrid, but into other microgrids as well, for situations where a microgrid controller may be transacting energy with another community, with another microgrid controller. So you have these peer-to-peer, device-to-device interactions going on at multiple levels that are too complex for really a system operator to really create a security policy all around this. So we automate all of this through a very dynamic approach based on an identity, based on enforcing interactions down to the machine level, and while creating the policies in a very central location through a single screen. And I also want to mention there that these interactions happen quite frequently, right? You have energy offers, demands, settlements that are happening, and they need to be reconciled against, not just the financial transaction itself, but actual, physical power, whether it was actually released. Was it released based on what was offered or what was demanded? How much of it was released? So all of that requires all these, the data to be recorded for reconciliation later, and that record needs to be highly immutable. It needs to be definitive, very objective, and this is where another reason why they like our Xage Security Fabric, not only because we create trust for the devices, control the various interactions, but also record all the data in a very objective, immutable way, so that it can be trusted and relied upon.
What I just heard you say sounds like it's drifting back into the domain of sort of traditional blockchain. It's not just permissions and authorizations that you're managing. You actually have something more conventional blockchain-wise in there in terms of recording business transactions? They're
energy exchange transactions. If you have a tamper-proof, immutable, peer-to-peer data sharing solution, we have customers who are interested in recording, power data. They're interested in recording actual access data, variety of data. In some cases, also demands and offers, which is you could consider financial data, but it's really business data.
Andrew, I could use some clarification on something. It appears to me that for the majority of this podcast, Roman was describing centralized blockchains, private blockchains owned by specific sites or vendors, whatnot. Now he's using terminology such as peer-to-peer, which is the diametric opposite of a centralized blockchain. There wouldn't be a single authority. So I'm wondering how we moved from one to the other. Is it just that the Xage Fabric offers sort of both implementations, or what?
Well, again, we chatted afterwards, and if I recall correctly, Roman said that the same Xage Fabric does support both the permissions ledger and other kinds of transactions. There's not two different kinds of blockchain going on. It's the one fabric that supports both kinds of ledgers. But if I understand you correctly, the rest of your question is kind of coming back to the topic of consensus. In Bitcoin, nobody trusts anybody, and so 50 plus 1% have to agree. In my understanding, there is no authority in Bitcoin. You don't trust anyone. But in my understanding of the authority-based blockchain, there are authorities. Not only there are authorities, but you know who they are. You know who these machines belong to. You know who's authorized these machines. So if a power producer signs off on a block in a ledger saying, here's how much money I am offering the power for, once the authority for that producer has signed off on the ledger, they can't take it back because the consumer, the power consumer, has a copy of that signed block. If the power consumer signs the offer block, they can't take that back. If the producer has a copy of the doubly signed block, they know that the consumer saw the block and saw the offer and signed the signed offer. You can't do that with Bitcoin because there is no authority and there's no identity. You don't know who anybody is. In the Xage Fabric, in my understanding, because you know who's deployed these things, it makes all the difference in terms of signing and countersigning and winding up with a ledger that you can't take back. But we're coming up on the end of the podcast here. Let's go back to Roman for the last word. Well, this has been very useful. Thank you. We like to leave our guests with the last word. Is there a thought you would like to leave with our listeners?
Sure. I would encourage folks to visit Xage.com. There are a number of white papers down there that explain what I just said in a far greater detail. But also, we have a Fabric preview that's downloadable implementation of Xage Security Fabric that installs right there on your laptop, where you can give our solution a test run. It demonstrates ability to do all the various access control methods, machine to machine, user to machine. And it installs a blockchain implementation to do so right there on your laptop within just a few minutes.
I'd like to offer a last word here, which is that the blockchain that Roman's described here doesn't sound very much like the blockchain that I'm used to, that Bitcoin was originally founded on. But I do think it sounds very interesting, and I'd be interested to see where we go with it in the future.
Yeah, I mean, I subscribe to some academic journals, and there's been countless articles in recent years about countless different variations of the blockchain. And, I think what Roman's described here is a variation of the blockchain that is relevant to industrial security. Words I never thought I'd hear myself say. I thought that, the blockchain was Bitcoin and industrial was industrial and never the twain would meet. But, here we are. It's a new day. I learned something today. Thank you, Roman.
All right, that'll just about do it for this episode of our show. Thanks to Roman Arutynov for speaking with you, Andrew, and thank you, Andrew, for speaking with me.
Always a pleasure. We'll catch you next time, Nate.
This has been the Industrial Security Podcast from Waterfall. Thank you all for listening.